So last time we have commented on the need of a control loop for executing motion, desired motion for our robots. So we assume that we have made a smart planning of the trajectories, either in the Cartesian space or in the joint space. And then we mentioned that in order to reproduce this in practice on the robot itself, we need to close some sensory feedback. So the minimum requirement is to compare the desired motion with the actual motion as sensed by your sensors. And the least requirement is having a joint encoder so that we can know the actual configuration of the robot, and we can compare this with the desired motion in the joint space, or we can compute the direct kinematics of the task and compare this with the desired one. Or we may also have censored directly at the Cartesian level, for instance, a camera, and then we can make a comparison between the actual pose of the end effector and the desired one, and generate an error. And this error will correct the nominal command of motion. Remember, the commands are always in the joint space in order to bring this error to zero. Okay? The nominal commands are exactly the output of our trajectory plan. And we mentioned that this type of kinematic control, which neglects any mass inertia distribution of the robot, just looked at the kinematics of the robot, is performed either in the Cartesian, closing an error either in the Cartesian space or in the joint space. And then we have presented a first simple example and then a more sophisticated example, but still of a 1 degree of freedom system, the one that you see now on the slide, in which we set the limits of performance to this kinematic control approach. Namely, we mentioned that if we don't require too much acceleration and if the speeds are limited, the inner low-level control loop is able to reproduce whatever kinematic command we are giving. Typically, we're giving velocity command, but in principle, we could integrate this velocity command into a position command, or we can plan motion at the acceleration level, so we generate acceleration command. But in any case, we don't consider ever the dynamics of the robot. This will be a task in the second course of robotics. So with this in mind, if the required performance is not too demanding, then this loop works. This approach, leaving the dynamics to a low-level control loop and planning and controlling only at the kinematic level the robots. And this was a block diagram that we have seen. We plan things as if the low-level controller is ideal, which is the lower block in this simulation diagram. The upper block is, in fact, the real behavior with the same kinematic controller, and internally, the green block is the robot, in this case, a simple pendulum with its own dynamics, so with this inertia, gravity, if needed, friction, and so on. And low-level control design in such a way that the reference velocity command in this case is being reproduced. The trajectory generation block is on the left-hand side, the light blue block. And in this case, it generates both a velocity, which is integrated and then generates also the position. The velocity is used as a feed-forward. The planned velocity is a feed-forward. And the position, the actual desired position, is compared with the measurement of the position of the robot. And this is done at the joint level in the most simple case. Okay, see, was the scheme. This was the particular low-level controller, which was a PI velocity feedback loop with an acceleration feed-forward. So you can see that I played around with this. We added the torque saturation at the end because the output of this controller is, in fact, the torque that the motor needs to produce, but the motor has a maximum capability, so we included in this simulation a saturation. While in the blue blocks, you see a very simple representation of the dynamics of the robot. You see the M is the equivalent inertia, which includes the inertia of the link and the inertia of the motor. The MGD sign of U is the gravity effect. Small m is the mass, g is the acceleration of gravity, 9.81 meter per second. D is the distance of the center of mass from the base of the joints where the axis of rotation is placed. And this would be the model below. So you see that we have isolated the acceleration. And here we don't model the mapping between velocity and position because this is a outer integrator. Now we just would like to make sure that with this low-level control, the output velocity at the joint follows the reference velocity that we are giving to the low-level control, so the one that we command. But in fact, this is going to be translated into a torque or equivalent to a commanded acceleration. Okay, so this was a review of what we have done last time. Now, let's see how this simple example generalizes in the control loops of industrial robots. In particular, that class of robots, the large majority, that has closed control architecture. So structure where we cannot access and modify the low-level control loops and impose directly currents or torques to the joints and so on. There are new generation robots which are called torque-controlled robots because you can command in some way, more or less directly, the torque that the motor needs to produce. And these are typically needed for interaction with the environment and in particular for human-robot interaction and safety, because controlling the torque allows directly to control the interaction forces. Okay, so how are they done in general? And this is nothing else than the generalization of this simple Simulink block that we have seen so far. So we start with the robot, and in particular, we start with the robot joint by joint. So joint by joint, in the sense, in the actuator space, where the actuators is located, and we assume for the simplicity that there's one actuator for each joint, even if it's not located directly at the joint. There are other cases where multiple actuators, typically two actuators, work in cooperation for moving two joints. So there are closed kinematic structure where this happens, but you can also you can always invert this mapping and assume one actuator for each joint. Okay, so we look at the joint, we have an actuator. There's a first loop on the actuator side, so it doesn't exit the box through which we model the actuator in this diagram, which is a current loop. So the current is being sensed by an analog device internally to the motor and compared to a reference current, so that the difference between the reference current and the actual current goes to zero. And in this way, we are generating torque. With the torque, we move the robot joint. So this is the most inner loop, and it's an analog loop, so we don't have to worry about the sampling time. This is continuously, in a sense. Okay? And of course, depending on the gains that you use in this loop, you may have a very large bandwidth to work with, which is good. Now, the next level is an analog or sometimes a digital loop on the velocity, which is exactly what we have done before. So we neglected the presence of a current loop in the previous simulation, and we assume that whatever current is being produced is exactly proportional to the torque, and the torque is what we modeled in the previous simulation. So here we measure the velocity q dot of the joints, and in particular of the particular joint. So local. There's no need of transferring measurement from one joint to the other or going through the central architecture, although this is what is being done. And we compare with some reference, which is not yet listed there. There's only a minus sign, but on that summation block at the beginning, there will be a plus with a reference velocity, and you generate an error on the velocity, and then here I express the controller as a linear controller. So this is why I'm using the Laplace notation. So it's a transfer function, gvel of s. In fact, it could be either proportional, so there's no dependence on s, or an integral or proportional integral controller, like we have done before, so which means that in the domain S, the integration, so in the Laplace domain, the integration is replaced by a factor 1 over S. Okay, so this guarantees, and if it's analog, this guarantees, again, with sufficient bandwidth, that the reference velocity and the actual velocity will coincide as soon as possible. Indeed, you may not have a measurement of velocity, so you see that this q dot, if you have an analog loop, should be provided by an analog device, so a tachometer or a resolver, which is a position measurement, an analog position measurement, and you use some derivation of this signal. Or if you're using, as nowadays it's the common solution, digital encoders, then from the encoders we know that we can extract also some information about velocity. In this case, you have a digital velocity signal. Either you convert it into an analog one if you want to use an analog loop, or you keep it digital and you close the PI at the digital level. Okay. So, but the actual result is all these blocks at that joint is seen in the ideal case, or at least for planning or for designing the remaining part of the controller as a simple integrator. Okay. So between the reference velocity and the actual position. This is what we have done also in the previous case. Now, what is certainly digital is the outer loop, which is digital feedback on the position area. So you compare Q with the desired of T. This may be I mean, your trajectory, or even just a constant reference if you want to attack a regulation problem. You don't care how you get to a certain configuration, but you just set the final value for each joint. If you care about the trajectory, then you have also velocity, and you can see that this scheme includes velocity feed forward, which is there even if the error on the position is 0, plus an action, which is a feedback action on the position error. And you can react with a simple proportional control to that. You may include also an integral term here. Very rarely at this level you include also a derivative term. So you use a standard PID control. We have already commented on that for those who knows. Otherwise, just look at Wikipedia if you wish. And these are subclasses of a PID where you turn off the derivative term or both the derivative term and the integral term, and you are left only with a term which is proportional to the current error. So the error at that instant of feedback loop, and you see that there's a separation, what is internally and what is externally, which is what you can implement on your computer and then interface this with the low-level controller of your robot. So you're sending reference velocities, which are a combination of the desired velocity and of some term on the error. So this is introducing feedback. So one thing to be noticed is that after all, although we are moving at the same time all the joints, this control law is typically decentralized. It means that the command that we're giving to the ith joint, low-level controller, is purely local. It does not depend on what the other joints are doing. So the coupling, if we are coming from a desired Cartesian trajectory, we have inverted the Cartesian trajectory with the differential kinematics or with the inverse kinematics in terms of position. And this is where we have uncoupled the things, because then we have a reference for a desired motion for each joint. And we keep this decentralization also in the control. Now, nowadays, this is not so a big issue because everything is centralized, computing power is very large. But in the early days, when we were designing analog control devices, or even in a prototype, we were building controllers locally to each joint and to each actuator, then the fact that you had a decentralized solution was very convenient, because you don't have to let a data bus going through your system and distribute all the data and collect all the data, bring it to a central computer, and so on and so on. So I would say that nowadays, especially if you're a robotic hobbyist, so that you build your own device, you use Arduino or other system like that, then the fact that you can decentralize things is still very convenient. Okay, now we have two main slides which correspond to two main approaches. This is very fundamental and very important. So now we design the kinematic control, so the outer loop, the one that assumes that internally the robot model is just a simple integrator, one integrator for each joint. So this is written in a vector form, but in fact this is a bunch of parallel integrator, one for the joint 1, another for joint 2, and so on until joint n. So it's the green block that you see. This is the model that we assume as ideal for our robot in order to design the outer loop, which is of the purely kinematic type. Now, the first scheme, and the simplest one, is kinematic control of joint motion. So remember, I'm insisting on that. We always command joint motion, but where do we generate the error is important and makes a big difference. So here we are generating the error at the joint level. In fact, if you look more carefully, you see the output of the robot is the measurement of Q. You feedback this measurement and you compare it with the output of the reference generator, so with the QD, and there you generate an error, which is an error in the joint space. And then you react this error with a matrix K, a positive definite matrix, often diagonal, because you want to preserve this decentralization, so this decoupling of control design joint by joint. And to this, you add the desired velocity that you also pick out from the reference generator. So the Q dot that you're commanding, and you're assuming that this will be also the actual, so the Q reference dot that you're commanding will be also the actual Q dot. This is why there's no special subscript to the Q dot in front of the green block, is your actual control. So you're giving this as a reference to the low-level controller and to the robot, which is inside this green, nice ball. Okay. Indeed, the robot starts in a given initial configuration at time 0. So Q0 is the initialization of this equivalent integrators. The green block on the left-hand side, the yellow block on the left-hand side is the reference generator. And here, I'm assuming that eventually, you're always starting from a task which is defined in the task space, which normally is the Cartesian space. Here, I'm using the P notation. This suggests position, but it may be also a pose. It may be an R vector, how we call it earlier. So a task vector with some desired motion for it. So we always start from there, which means that at the level of trajectory generation, if we want to design a feedback loop at the joint level, we need to generate, in any case, a trajectory or a reference for the joints, which means that if we start from P dot desired, and we assume that this is a square problem, so we have as many task variables as joints, so typically m equal n equal 6 for a position and orientation in the Cartesian space. So we invert the Jacobian, and we generate q dot desired. Of course, the Jacobian needs a desired position to be evaluated before being inverted, and this is taken not from the actual robot, but from the position that we are generating. So we start at the differential level, we invert this, and then we integrate the velocity, the desired velocity, to get the desired position. And in this integration, of course, we need to initialize the desired position, and then we continuously generate this. This can be done offline or even online if the desired velocity is something in the Cartesian space, is something that we don't know in advance, but we generate from sensor data. Typically, if the end effector needs to move in an environment and to reach some final position, but avoid any obstacle that may move around the end effector, so the desired velocity is being changed online in a sensor-based fashion, so this inversion is being done online. But this is not the standard situation in which you desire to close the loop in the joint space. In the joint space, you typically have the trajectory pre-planned, even if it's pre-planned at the task level, and you do this inversion offline. What is the advantage of doing this inversion offline? That if you encounter singularities or problems, you can decide what to do and what is the best way of handling this singularity. You can do a damped least square, a pseudo-inverse, whatever, but you have plenty of time to do this until you get a complete profile for QD and for QD dot, which is what you will use in real time. Okay, what more? Here you see some shaded block toward the end, the F of Q and the J of Q again. These are the direct kinematics and the differential kinematics evaluated with the actual value of Q. So you can always compute the direct kinematics once the robot starts moving, and also the actual velocity once the robot starts moving. But in this scheme, this is not used for control, because the only thing that you use for control is the actual measurement of the joint configuration Q. Okay, so this is the scheme. Now we would like to analyze if this makes sense, if these schemes in particular will perfectly reproduce the desired trajectory QD of time in the nominal case. So if we start matched with the initial position to the desired initial position, and if not, so we have an initial error, or we have an error at any time due to a disturbance that has shifted away my robot from the desired trajectory, if we are able to recover this error. And how do we recover this error? How fast or how good? Okay, so we make an analysis, and we make an analysis starting from the error. So the error is defined in the joint space. This is why this kinematic control scheme is called joint kinematic control, joint level. Now, the error is QD minus Q. Indeed, we would like to see what is the evolution of this error. It may be different from 0 at time 0 if we have an initial displacement. So we are not starting at the desired configuration. The trajectory is starting away from where the robot is in its home position. Typically, you may have this situation when the robot is at rest in some home position, and all of a sudden you see an object that is moving and you want to track this object. So you have an initial error. So you may have or may not have this initial error. In any case, in order to understand what will do the error in the future, so how it will evolve, just for analysis, pay attention. We are not computing this in real time. It's just what we are computing in real time is the Q dot equal Q dot desired plus K times the error E. This is all we need to know. So in order to predict what will be the evolution, we look at the time derivative of this error vector. Remember, the error has the same dimension of the joint space. So E dot, we just take the derivative of the previous expression, is Q dot desired minus Q dot. And now Q dot is what we are commanding. So now we look at the block diagram, if you wish, and you see, and you replace Q dot with your feed forward plus feedback. And now you understand why we need to add the feed forward, because the feed forward term, which is Q dot desired, is there exactly for canceling the other term in this expression. So that we are left with a minus sign, K times, again, the error. So we are left with an expression which is minus K times E. And if K is taken as usual, diagonal, you can analyze component-wise this equation. It's a linear differential equation. For joint I, you will have EI dot, so the derivative of the error at that joint is equal to minus KI, the diagonal gains at joint I, times EI. And you can solve, I hope you can solve this equation in closed form. You will see that this is an exponential behavior. If K is negative, is positive, sorry, the minus K is negative, so this exponential is converging to 0, which means that you will converge to 0 error, if you started with an error different from 0, in an exponential way. And the faster, the larger is the gain K. Of course, you cannot use a huge value for K, because you would then violate the assumption that your robot model can be packed into a simple integrator. Then you will excite the things that you have neglected in the modeling and in the closed-loop modeling of the low-level controller. So you assume that the low-level controller is ideal. In fact, it is not. So this is why I introduced these examples in the beginning, to understand why we cannot increase arbitrarily K. But indeed, the best choice would be the largest K possible, until we see that the behavior is not what we expect. We are getting into the bandwidth limit of our low-level control loop. So this means that the error goes to 0. It means also that if we start with 0 error, the error will remain 0. Because the behavior is exactly that of an exponential, and the solution is E of 0, the initial error, time an exponential of minus KT, okay, over time. So this is a very nice result. We know how fast we could recover the error. Now, during this transient, indeed, remember that an exponential will go to 0 if it's converging when t goes to infinity. In practice, if you take 2 or 3 times the time constant of the exponential, which is the inverse of k, so 1 over k, then you're practically at 0. So even if mathematically the exponential goes to 0 only at infinity, in practice, 2 or 3 constant time constant is equivalent to being at 0. Okay, so this is a very nice result. Indeed, each joint goes to 0 independently, which means that if you start with all joints matched except one, then with this control law, the joints that are matched will continue to be matched to the desired motion, in the absence of disturbance indeed, while the single joint that was not matched will recover its error exponentially. So you have a perfect decoupling of behavior. The fact that one joint is recovering its error does not affect the motion of the other joint. And this is thanks to this type of scheme. Now, indeed, if you have an error in the joint space, you will have also an error in the Cartesian space, unless you are in a strange singular configuration and you're in the null space of the Jacobian, so you're in a configuration that is associated to the same end effector position, but in fact you are in a different value for the joint space. But this is a special case that we here don't consider. First, because we have a square situation, and second, because we assume that the Jacobian is invertible. In fact, in the trajectory generator, we have the inverse of the Jacobian. So when you have a joint error, you will have also a Cartesian error, okay? So if we define the Cartesian error as the difference between the desired PD and the actual P, and now for analysis, we are using the P and P dot that we compute from this block diagram, just for analysis, not for implementing the controller again. Now we would like to ask ourselves, is the error going to zero at the Cartesian level as well when the error in the joint space is going to zero? The answer is yes, indeed. But how is going to zero? That makes a difference, okay? In fact, just look at the definition of the error in the P coordinates, so at the Cartesian level, if you wish. We have a PD minus P. We look at the evolution in time, so we have a EP dot. This will be the derivative of the two terms, so PD dot minus P dot. Now, PD dot, you see from the reference generator that it's taking as input PD dot and generating QD dot. So vice versa, in the presence of invertibility, PD dot will be J of Q desired times QD dot. While P dot, if you look at from the block diagram, will be J of Q of the commanded Q dot, which is Q dot desired plus K times the error in the joint space. Now, unfortunately, you see that in this case, you cannot cancel the two terms with the Jacobian, because in one term you have the Jacobian evaluated at the current configuration, and in the first term you have the Jacobian evaluated at the desired configuration. And if these are different, these two terms do not cancel. However, you may assume that you're close enough and do an approximation. So you can approximate saying that Q is locally around Q desired. So you can make a Taylor expansion starting replacing Q in the Jacobian, which is the only nonlinear term in this expression. You linearize this around Q desired, and you throw away any product of higher order terms. So this is just saying that you can get rid of the first term with a part of the second term, and you are left with something which can be written in the following form. There's a minus sign, there's a Jacobian at the current configuration, times K, and similarly, the error QD minus Q, an error in the joint space, so a displacement over time is a velocity. So this displacement can be associated to the inverse Jacobian of a displacement, which is nothing else than the error in the Cartesian space. So you have this final approximation. You say that EP dot, so the way in which the error evolves in the Cartesian space, when I'm controlling the robot in the joint space with this kinematic control, is approximately minus J of Q times K, J to the minus 1 Q, E of P. So if you have an error EP is 0, then it will stay 0. It's exactly the same situation as in the joint space. But in general, there will be a coupling of error components, because even if K is diagonal, the product by J to the minus 1 will make this a full matrix. So if I have an error in one component that is going to 0, but before going to 0, it will affect the error also on other components that may be 0 from at the start, but then will become different from 0 and then again converge to 0. So you will have a coupling at the Cartesian level, which is not very convenient if you wish. But if you don't care about what is going on during this transient at the Cartesian level, you just care to reproduce as good and as fast as possible your joint trajectory, then this is the best way of working. And another aspect which is advantageous in this is that in real time, you never invert the Jacobian. So if you cross singularity in real time because you're a bit far off your desired trajectory, you assume that the planned trajectory will never encounter a singularity because you are inverting J to the minus 1 QD, so you have done this offline. But online, because of the error, you're not exactly where you expect to be. You may get closer or cross a singularity. Nothing happened with this scheme because you're commanding directly in the joint space, and you're not inverting the Jacobian in real time. So this is another advantage of this. Okay, what is the alternative? The single alternative in this case is to do kinematic control of the Cartesian motion. So at the Cartesian level, or more in general, at the task level. Now, I'm not say again the same concept. So you start with the same robot model. You assume that this is ideal, so it's a simple integrator joint by joint from a command Q dot. You see that we're always generating a command Q dot. So this is now clear. But now, from the current Q, instead of feeding back the Q, you're feeding back the value of the Cartesian quantity or task quantity. So you're computing the direct kinematic f of Q with your model. You have a P, and you bring this back in feedback, and you compare with the P desired. So if you started with the same type of desired motion in the Cartesian space, so you have a PD dot as before, now you see that the reference generator is not doing anything other than integrating this to generate also the associated P desired. So you have a P desired and a P desired dot coming out of the reference generator, which is now much simpler than before. And of course, in order to integrate the Cartesian velocity desired, you need to know where you would like to start from. So you have an initialization P desired of 0 in that yellow block. So you take P desired, you compare with P, and you have an error in the Cartesian space. So what we have called before E of P. So it's a different error than in the joint case. And you're reacting to this error with a diagonal, typically diagonal, but certainly positive definite matrix. So if it's diagonal, this means that all the elements on the diagonal are positive. Plus, you're using a feed forward, which is now the velocity in the Cartesian space, exactly like before. So feed forward plus feedback. But both the feed forward and the feedback are objects that live in the Cartesian space, and in fact, you react to an error in the Cartesian space. Now, being this equivalent to some reference velocities in the Cartesian space, in order to get to the command in the joint space, so the velocity Q dot, you have to invert the Jacobian. Now, invert, we are assuming is square, non-singular, and so on. If it's non-square, we can use pseudo-inverse instead of j to the minus 1. But in any case, we have to worry about singularities, because if we are getting close to a singularity, this will generate a huge command Q dot, even if the error is small or the commanded velocity P dot desired is small. And in that case, we have to implement some real-time correction. Pay attention, even if you're not crossing the singularity, we have seen this effect, we're getting close to a singularity. When Q dot increases suddenly, we have two things. It's not only that we are violating the limit of Q dot, so of the actuators, but we may violate the assumption that the internal low-level controller is an ideal one, because large variation of Q dot means large acceleration, and then we may not be able to reproduce this sudden variation of commands into the actual velocity. So the ideal assumption that we have just an integrator between the commanded velocity and the position is no longer true. So we definitely have to deal with handling the singularities in real time in this case. So we have just described the whole structure. Again, we don't use the Jacobian as in the computing P dot, because P dot, we are not using P dot. Both kinematic control scheme that I'm presenting here assume that we are commanding joint velocity. Indeed, it's a simple exercise that I strongly suggest you to do, to make a scheme, either in the joint space or in the Cartesian space, that does the equivalent of this, but assuming that we command joint acceleration, so Q double dot. We need to bring everything at the second order. We had to close a feedback term, both on position error and on velocity error, since we have moved the command to the acceleration level. Okay. So at this point, instead, we return to the first level kinematic control, now in the Cartesian space. One more comment on the last block. I'm saying that we are doing feedback from the position. And in this block, we compute the position of the end effector by direct kinematics, or the position of our task variable by the direct task kinematics. So, which means that we are still measuring only Q. Indeed, if you measure directly P in this case, you can get rid of f of Q. You know that there's a sensor, I mean, there's a f of Q, but you don't use this in your controller because you're measuring directly P. So the simplest case, suppose that you have a 2R planar arm and you have a camera overlooking the plane of motion. With the camera, you can trace the end effector position at any time. So from the camera, you get the position P. Even if, let's say, you just put the light on the tip and you shut off the ambience light, so you don't see anything else than the end effector. So you don't know if this is a 2R robot or whatever it is, and where the configuration is. You just see the P, and you're feeding back P and compare with the P desired. So you can do this with a sensor which directly measure the variable under control. Those who are expert of automatic control knows that if we measure directly the quantity that we would like to control, we are more robust. We add noise in the measurement, but we are more robust to uncertainty. In fact, this means that if you have some uncertainty in your direct kinematics, so your robot is not well calibrated, then of course, what you measure Q and you compute through an uncertain kinematic model, you compute P, then this P will not be the actual one. And will bring P to the desired value, but in fact, you're bringing the wrong P to the desired value. So you don't have robustness in this sense. Okay, but this is an advanced topic. We will leave it on the side. So summarizing, you can measure Q and compute P through the direct kinematics, or you can measure directly P, and the analysis is exactly the same as long as the model is correct. The kinematic model is correct. So let's see what happens to the error in the Cartesian space, so to EP in this case. We do the same analysis as before, but now we start directly with the quantity that is being, that we are reacting to with this scheme. So we are reacting directly to the Cartesian error. So EP is PD minus P like before. Let's look at the evolution is P dot desired minus P dot. Now P dot can be evaluated from the block scheme. So you see that above, just for analysis, P dot is equal to J of Q times Q dot. But Q dot is J to the minus Q times the feed forward of the Cartesian velocity plus Kp, the error in the Cartesian space. So here you see that in this expression, you have minus J of Q dot, which is P dot, but Q dot is J to the minus 1, the expression in the last parenthesis, and J times J to the minus 1 cancel. And you remain with P dot minus P dot desired minus P dot desired plus Kp, the error in the Cartesian space. So the 2 P dot, again, the need of a feed forward in order to eliminate that term. Otherwise, you cannot say anything about the sign of this term or the behavior. So you are left only with a minus sign times Kp, Pd minus P, which is nothing else than the error in the P coordinate. So you have, again, minus Kp times Ep. Okay, so exactly the same situation as before. Remember that now Kp works in the Cartesian space, so it's a matrix gain. Again, you can choose diagonal. certainly positive definite. So component-wise, component by component, you have an exponential transient going to 0 as fast as possible by enlarging the gains on the diagonal of this KP matrix. And you have a perfect decoupling. If you start with one component of the Cartesian space, which has 0 error, and the other has no error, has an error, then during this transient, the one that starts with 0 error remain at 0 error, the other will converge to 0 exponentially. There's no coupling in the Cartesian space. Indeed, if you look at the equivalent joint space motion, and if you are starting with one component which is 0, has 0 error, and the other component which has not, then during the transit in the joint space, everything got mixed. It's exactly the opposite situation. When you decouple in the joint space, you have coupling in the Cartesian space. When you decouple the behavior of the error in the Cartesian space, you will have a combination, a mixed behavior in the joint space. Okay? So these are the extra comments, so exponentially as before. So if we start with 0 error, we will remain with 0 error, and this is true both in the joint and the Cartesian space. Otherwise, we will have this exponential convergence. We need to compute online the inverse, and indeed, everything has to be done in real time, in particular, the handling of singularities. And again, here you have to switch to damped least square or some other form of modification of your differential inversion. And you have to do this in real time. You don't have much time to decide what is the best to be done. Any question on these two schemes? So let me add that, okay, here I'm saying Cartesian motion, but any variation of this to move to a task space is feasible. In particular, you may decide to have this decoupling not in the original x and y coordinates. Let's say, consider again our 2R planar robot. So it's moving on a plane xy, so either you control by feedback Q1 and Q2, or you control by feedback x and y. But you may also introduce a rotation on the end effector, and you would like to decouple the behavior of the error not along x and y, but along the x and y axis of a rotated frame. You have to include a rotation in this expression and do the computation. There's one exercise, one exam, that is doing exactly that. And so it's important. Why you would like to care about that? Well, if you have to track a line in the Cartesian space, which is skewed with respect to the x and y axis, so it's a generic line or a segment of a line. Okay, I will answer to the question in a moment. So if on the line, you really care differently if you're getting off on the side or if you have an error along the path itself. So you may wish to react more promptly to an error which brings you off the linear path, while if you're a bit too in front or too back on the line itself, you will like to recover the error as well, but maybe with a different dynamics. Okay, so in order to achieve this type of decoupling, decoupled behavior, you have to rotate yourself and put yourself on the line or on the tangent, on a frame, which has a tangent direction and a normal direction. So you like to react differently from in the two direction, which is like the Cartesian case, but now you have the task rotated in the proper frame. Okay, so this is why frames are so important. So let me go back to the question here. What happens in real time if we detect that we are getting close to a singularity? We stop? No. I mean, we stop if we are not able to do anything else. But we switch on one of those techniques. The most common one is the damped least square. So instead of inverting the Jacobian in the square situation, or even in the non-square situation with the pseudo-inverse, we switch to a solution. We introduce the lambda factor, the damping factor, and we have an explicit form for obtaining the command. So we will tolerate some error at the Cartesian level, but it's a transient phase. And the presence of the feedback, if you go back to the simulation that we have done, comparing j to the minus 1 with j damped square, in the case of a 2R, we've seen that when we're getting close to a singularity, the j to the minus 1 grows to infinity, or to a very large value if we don't set saturation, while the damped square has a very smooth behavior in the joint space, but it introduced some error, and this error is exactly the one that is being recovered by this feedback law. So if you go back to the slide, I added the note, said this error is being recovered as fast as possible by the presence of Cartesian feedback. So this is what we do. We activate, so monitoring the least singular value of the Jacobian, so a distance from the singularity, if you wish, the determinant, but we have already commented why the determinant is not a good measure of distance to a singularity, although it goes to 0 when the Jacobian is singular. So monitoring this, when it grows, when it falls below a threshold, we activate the lambda. And we activate the lambda in a smooth way. We keep this activated until we see that the Jacobian is again, the Jacobian itself is again growing out of the singularity, and then we switch it off so that we are able to recover the error thanks to the feedback part of the control. Argenziano, did I reply to your question? Okay, fine. So let's move on and let's do another simulation. This is an old simulation, so this is an old Simulink block diagram. Even the aspect of the icon have changed, but this is not really relevant. You can repeat this by yourself with the latest version of Simulink, which is, by the way, available to all registered students of Sapienza. So here we consider a 2R robot with unitary link length. So again, the most simple case. Extend this to the 3D and to presence of prismatic, revolute joint, combination, and so on. We consider two types of tasks. Executing a segment of a straight line or doing a circular path. And in both cases, we don't care now about smooth timing law. We just fix a constant speed. Indeed, if we to reproduce a constant speed from the beginning, it's physically impossible if we start with 0 speed. But since we are commanding velocity, we don't care about this inconsistency. We will integrate the closed loop system. So we have the robot kinematics. So we are assuming no dynamics here. We're assuming an ideal model for the dynamics, that the low-level control loop works perfectly. So in the simulation that you will see, I don't exploit the fact that we may run into the limited bandwidth of our low-level control loop. So we consider ideality. So then the kinematic controller, it could be a joint space or a Cartesian kinematic controller. I think it's more interesting to look directly at the Cartesian kinematic controller. So we have a trajectory generator on the left-hand side. We generate both the desired P and the desired P dot, so the velocity. And this enters into the kinematic controller together with the Q, because we need the Q for evaluating the Jacobian and the Jacobian inverse, and the actual P, which is the position of the tip. And this is computed from the direct kinematics. And then we generate a Q dot reference, so a reference velocity, which will be by the kinematic control in the Cartesian space, which will be the sum of the Cartesian velocity desired plus Kp times the error in position, so Pd minus P in the Cartesian space. And you see that I also bring this block, save the variable in the workspace for later plotting in the MATLAB environment. So I'm saving also P dot, so the velocity of the end effector, although I'm not using this for control. In fact, I'm not feeding it back at all. In this old schema, I was saving also the clock. Now the MATLAB saves directly the variable with a timestamp so that you can plot them in time, even if you're not using a constant integration step. But you can do the same, and you can save the quantities as array and not as a timed variable. And indeed, I need to integrate this differential equation in the closed loop. These are still nonlinear. I need an integration method, and I can choose one from the menu of Simulink. I prefer to use Runge-Kutta, which is ODE45, with a fixed step, not leaving the integration step to the system to decide, but I'm fixing so that I know exactly what's going on. And I fix an integration step at 1 millisecond. This is not necessarily the update rate of your commands, although if I'm not modeling this, for instance, I'm saying my Q.ref is being updated every 10 milliseconds, because this is what happens in reality. I'm not able to update my command every 1 millisecond. For instance, in the KUKA LWR4, if I do this computation of the kinematic control outside the low-level loop, on my PC, I have to interface my PC with the robot, and this requires 12 milliseconds per cycle. So I need to, if I want to simulate this situation realistically, I should hold my command for 12 milliseconds. Here I'm updating every millisecond my command. Okay. Still, we will see in the last simulation that what happens when this is no longer true. Okay, so this is the scheme. And if I explode the schema, it's very simple. I have MATLAB function doing the computation, so I don't need to model with icon and blocks all the trigonometric solution. The kinematic controller is, again, you see a comparison of PD minus P multiplied by the control matrix K, which is the KP in our case, adding the feed-forward term. And then I'm organizing in a multiplexer everything because I need to compute the j to the minus 1 p dot reference. And now you see there are two blocks added in the kinematic controller to make things more realistic. One is the saturation. So my velocity command, whatever it is, cannot exceed some limits. This tries to keep into account the presence of, the presence of limitation in the low-level direct control and also in the actuators. And another block which may be substituted or put in series to the previous one is a zero-order hold element, which means that I can simulate everything at 1 millisecond, but every time I generate a new command, a new reference velocity, I'm holding this for an interval of time, which is a multiple of the simulation. I can hold it for 10 intervals, for 20 intervals, for 50 intervals. If I hold it for 50 intervals, I'm having a 50 millisecond delay between when I command the system and when I command the new value. In between, the system is evolving, but I'm not updating my control. And this, I suspect, that may induce some problem. Okay. Now, the first task I will simulate, so the linear path I will simulate in ideal condition and with a saturation. And for the second task, doing a circle at constant speed, I will simulate it in an ideal condition and with the sample and hold. Okay. Now remember that when you do a simulation, a Simulink diagram, so this is a practical recommendation, but very important. Never put numbers into the blocks. Use always symbols. If you have a length, use L1, L2, and define the numerical value of L1, L2 in a separate MATLAB file from which you initialize all the data, and you can also run the Simulink block without opening it. There are special commands, the sim command, that will start the Simulink block without the need of opening and updating this. This has two advantages. It's parametric. If you decide to change some value, and this value appears in several points, then in this way it will update it everywhere. If you put numbers, and you have to remember that this number corresponds to something, if you change that number, you should change accordingly also a number in another block, it will become a mess. And then also for understanding what's going on. If you just look at, you open a block diagram and you see only numbers, you don't understand what they are coming from. If there's an error, so for debugging is also very important to do that. So here I'm using some MATLAB-defined function, the Dirkin Jack, and then I'm using the inverse function of the library of MATLAB for inverting the Jacobian. These are simple codes that are expressed like this. For instance, here you see that the Jacobian is just, I'm passing the value of Q, which is coming from the block diagram in Simulink. I'm defining the global L1, L2, which has been defined in the initialization, which you see on the left-hand side. And then I compute the elements of the Jacobian. Very simple. Then this will be passed as output. The next block will be an inversion, and so on and so on. So it's quite simple. So what are the data for the first task? So we have a straight line path to be traced at constant velocity that goes from an initial point x desired, y desired, which is 0, 7, 0, 3. And I have to move along this straight line with a constant speed of 0.5 meter per second only in the y direction, which means that the x desired will remain at 0, 7, and this is a line along the y-axis from 0.3 for 2 seconds at half meter per second for, so I will trace a 1 meter. So I will go from 0.3 to 1.3 meter along the y direction. So this is the desired path, and actually the desired trajectory, because I'm specifying a straight line path and the timing law, which is very simple, constant speed. So I have a full trajectory. And do I start at the beginning of this trajectory, of this path, so with 0, 7, 0, 3? No, because I'm setting the initial configuration of the 2R robot at minus 45 degrees plus 90, or minus pi over 4 and pi over 2. If I compute the direct kinematics, I have an initial error, which is minus 0.7, 0.3 meters. So I'm starting off both in x and y. I'm using as control gains the diagonal of 2020. So these are gains in the Cartesian space, what we have called before KP, but now it's irrelevant since we are only considering the Cartesian situation. So the first simulation will be without any limits for the joint commands, and the second will be will have some saturation. So I'm setting limits to the joint commands at 120 degrees per second and 90 degrees per second for the second. So we'll see what happens then. So here you see on the left-hand side a non-time behavior, because it's just the picture from above of what's going on. Let me see if I have, yeah. So let me move here. So here on the left-hand side, where is it? Okay, I'm coming slowly. Sorry. Here, you see the dashed blue line going up. The dashed blue line from 0.3 to 1.3 is the actual desired path. And you see where the actual path starts at time 0, PD of 0, and you see where the actual and effector position is at time 0, far off, and both in x and y. Clearly, the error in x is much larger than the error in the y direction. And then you see on the right-hand side some stroboscopic view of the actual motion. So I run the simulation, I record the cues, and then I have a simple MATLAB code that plots the configuration sampled over the whole trajectory. In fact, I need to sample them differently. The first phase, which is the transient phase, which lasts about 0.2 seconds, so 200 milliseconds. And you see from the initial configuration, which is the green one, the robot moves along the tracing the blue configuration. So it's approaching the axis. In red, I have plotted the end configuration as well. So this is the first phase, for 0 to 0.7, until the error comes to 0. Now the trajectory is moving, so I need to move at constant speed going up. And the second phase, for about 1.8 seconds, so a total motion is 2 seconds, remember, you see that the end effector will move along the vertical line, and you see some sample configuration in this stroboscopic view. Okay. Yes. So, sorry. So if we look at the time profile now, because those were not timed in sense. The stroboscopic was sampled, but I don't know how fast is this, although I've written 0.2 seconds and 1.8. But here I have over time, and the dashed blue line on the left plot are the desired Cartesian component. In fact, you see that the x-axis is being constant at 0.7, while the y value grows linearly at constant speed between 0.3 and 1.3. And in red, the continuous line in red, are the actual component of the end effector, and you see quite clearly that the transient is exponential. You see the way in which the error goes to 0, especially on the horizontal part, you see a clear exponential, very fast. The time constant is 1 over 20, because 20 was the gain, and the same time constant is the one on the y error, although you have to put yourself, rotate your head in order to see the exponential going to 0. Now, what are the commands? What are the control inputs? They are reference velocities given to the two joints, and you see that there's an initial phase where there's a huge value. In fact, there's one instant in which I'm saturating the pink profile, a very short time for QR.2, and then after the transient has passed, when I'm on board of the desired trajectory, I have the velocity that this trajectory requires, the one that I planned. So quite small compared to the huge value that I had, because I started with a very large error from the beginning and I have large gains. So I required a pushing action to bring me as fast as possible to the desired trajectory. So recovering the error, this is done in a very nice way, but the price to pay is huge commands. So nothing comes for free. So if I, okay, so these are the comments. If I now put the saturation in place, realistic saturation, what happens? So this is the simulation under saturation with a large initial error. And you can see, again, the straight line going up, the desired path, the actual path of the end effector, which goes to 0. The error goes to 0, but not really in a direct way. You see that in the first place, there's a divergence, in fact. So the end effector is going in the wrong direction and then recovers, and with some not straight path, I mean, it's getting to 0. And again, you have a transient phase which lasts longer now, 0.5 seconds, because it wanders the robot for a while, and then the trajectory following phase when the error has gone to 0. More or less, you see, when y is about 0.6, the error has gone to 0. Okay, when the red line touches the blue line. And once it's 0, it remains 0. Now, if we look at the time plots exactly as before, and we have set the limit, it was 120 for the first joint velocity, plus or minus 120, and 90 degrees per second for the pink plot, which is the joint velocity of joint 2. And you can see that in the first phase, we are saturating both in an opposite direction. So we are giving commands which are not the one that would bring us closer to the desired trajectory, so which will reduce exponentially the error. In fact, we are going in the wrong direction. And only when we exit the saturation, of the first joint velocity, but we enter soon after the saturation in the other direction. So about 0.4 seconds, we exit from saturation for both commands. And from there on, and if you compare what's happening at time 0.4, from there on, the convergence to the desired motion is exponential. So it returns to be exponential, as the theory says. But in saturation, we have a nonlinear behavior, so nothing can be said in advance. In this simulation, we see that after all, we converge, but something strange may have happened otherwise. Okay, so these are the comments. So let's look at the second simulation. Now, this is a circular path with constant speed. We place the center of the circle at some point in the Cartesian space with a radius of 0.4. The constant speed is 2 meters per second. So if you have a radius of 0.4, well, so you compute the length of the circumference to be traced at 2 meters per second. If you want to make 2 rounds, you have a total motion time of about 2.5 seconds. You can do this computation. Now, in this case, I show what happens if we start with a matched initial condition. So when the error is equal to 0. So we are in a configuration such that if I compute the direct kinematics, I'm exactly at the initial point on the circle. Of course, I have to decide where I start from. So the initial error is 0. So what happens when the error is 0? The error remains 0. This says the theory. The Cartesian error will remain 0. So I will trace the circular path with the desired constant speed of 2 meters per second. Who's giving me this command? The feed-forward term, because the feedback is 0, but the feed-forward is there exactly for doing this task. And in fact, if you update things at 1 millisecond, so at 1 kilohertz, you do the simulation, but as I said at the beginning, I'm updating also the commands every millisecond, so at this frequency, even if you switch off the feedback, so if you take kp equals 0, so you're just giving the feed-forward command, so you're just doing planning and controlling with the planned velocity without any compensation of potential error, we will see what happens. And then in the second situation, we will move to a realistic situation. So we are updating the command every 50 hertz, so every 0.02 seconds. So the commands are computed even more frequently, but I can update the computed command only every 200 of a second. So this is the duration of the whole command. And I'm not using feedback again. What happens? And finally, same story with the delay or sample and hold, or the update at the realistic rate of the commands, but using Cartesian feedback with 25 and 25. We use a slightly bigger than before. Okay, so let's see the result. In the first case, so no initial error. So you see at the bottom, the green initial configuration, the end effector is on the circle, is on the most far point of the circle. There the circle starts and goes counterclockwise, I would say, the trajectory. And you can see that there's perfect superposition between the actual motion and the dashed motion. Now, the red continuous line are the actual motion of the end effector of the robot. The dashed blue lines are the desired one. So you don't see any changes. You see a sinusoidal behavior. Of course, we are tracing in the Cartesian space a circle at constant speed. So we see sinusoid and cosinusoid, or sinusoid with some shifted initial phase, and this is perfect. If we look at the commanded joint velocities, now this q dot r1 and q dot r2, so this q dot r are nothing else than the q dot desired coming from the inversion of the p dot desired from the circle with the Jacobian. Everything is nominal, everything is matched, so there's no error correction needed here. In fact, you can see the stroboscopic view. It makes one round, the second round, the final configuration is shown in red, as in fact coincide with the initial configuration. Finally, the last plot on top is the evolution of the joint variables, so the integration of the commands. You see that these are periodic motion, but not sinusoidal. Why are they not sinusoidal like the px and py that we see on the left-hand side? Question. Anybody would like to answer this? Pose it again. Why are the joint variables Q1 and Q2, which are the evolution of the joints while the end effector is tracing a sinusoidal behavior, why they are not sinusoidal? I don't see you, so I don't see if you are sleeping or if you are speechless. Okay, why not? Because we have a nonlinear mapping between the joint space and the Cartesian space. These are trigonometric functions, which, by the way, are sine and cosine, so they are trigonometric, but of an argument which is also trigonometric. So as a whole, it's a nonlinear behavior. So they are periodic because we are tracing, the system is non-redundant, so we are tracing on and on the same motion, so we are periodic in time. And in fact, we are not encountering any singularities, so periodicity is automatic, but the behavior is non-sinusoidal. So this is the ideal case. So we are updating continuously, in fact, every millisecond. So this is simulation can never be continuous, but we are updating fast enough that we can merge this into a continuous behavior, the controller. So now, same situation, without feedback. What happens if we can update only every 200 of a second, so at the rate of 50 hertz, the command? And you see we start matched, but there's a progressive shift during the execution of motion. You can clearly see what happens to the control inputs. You can see that they are sampled and hold. So you see that they are piecewise constant. You can recognize some small interval in which they remain constant. Indeed, this is being integrated and the joint variables are exactly continuous as before, but they have a drift. You see that they are no longer periodic. In fact, if we look at what happens in the Cartesian space, we start meshed and then we drift on the outside, and in particular here, I'm referring to this situation here. Okay. So they are drifting once, closing the loop once, then doing the same turn. And if I continue, I don't know if this is drifting forever, but certainly this is not what we would like to do. In fact, we have not activated the feedback part here, relying only on the feed-forward. But if we cannot update the feed-forward fast enough, this is another big reason for closing a feedback loop. So for moving from planning to control. So we are recovering, we hope that this will recover the error, despite the fact that we are updating. So our analysis was made in a continuous time, when we write E dot equals sum. Now we are in discrete time and we have a delay. Does the feedback work? We will see that it works. But before, let me comment on this, sentence on the left, on the bottom left. So a drift occurs along the path due to the linearization error. What is the linearization? In fact, we are every time we are commanding a velocity which is along the tangent of the path. But this tangent change continuously. If we are not updating this tangent frequently enough, then we will clearly get out of the trajectory. This is why the error accumulates on the outside, or then which becomes then the inside when we turn by pi of the circle. If you had a straight line, you would have the same effect, but probably not so pronounced. Here, because the curvature of the path is large enough, then this error is felt in a more relevant way. Okay, so what if we close the feedback? Now you see that there's still a slight error. For instance, in the first plot, you can see that the red line is not perfectly superposed to the dashed blue lines. The control input are still piecewise constant. The joint variable, everything returns to be, these are two circles, so it's almost perfect with this 50 milliseconds. Now, one may think, well, you have chosen k diagonal equal to 25 and 25. Why don't double this value? Why not use 100 for each component so that you can recover this error faster, and then probably you will see no differences with respect to the continuous time update? Well, unfortunately, this cannot be done, because when we move into the discrete time domain, a system which in principle remains asymptotically stable for any value of the gain, like we have seen in the continuous analysis. We have written that the error E dot is equal minus k times kp times E, or in the joint or in the Cartesian space is the same. This is an exponential behavior, but assuming that everything works continuously. If I replace this with a discrete time version, I can see that even if I'm coming from a system that in the continuous time would have been asymptotically stable, in particular exponentially stable, I may hit an instability in the discrete time. And this depends on the time delay and on the gain. Of course, for a given time delay, there will be an upper bound for the kp before becoming unstable, or vice versa. If I fix the gain and I increase the time delay, there will be a lower threshold crossing which I will become unstable. So there are stability problems for discrete time control system that prevents me from getting better. Probably I could have increased a little bit, but indeed, if you reproduce this simulation, you will see that there's an upper limit to the gain. So performance are good, but not exactly like the ideal case for this 50 hertz. And this is one reason why we would like to enter into the system at the rate which is not limited by a slow communication channel. Because the slow communication channel in the feedback loop is a delay that tends to destabilize the behavior of the robot. Okay, so let me use this simulation. This is an old simulation made by one of your colleagues for his thesis many years ago. Now he's a professor in Brown University in the US. So this was a Fanuc, the picture, the nice kinematics. You can see there are many offsets here and so on. And he reproduced with an old version of MATLAB a simulation of a Cartesian task. Okay, so the simulation is made in MATLAB, but also the visualization 3D is made in MATLAB. You can use the robotic toolbox of Peter Cork to do a skeleton simulation, 3D simulation in MATLAB nowadays, or you can use a VREP, or Coppelia Sim is the new name, in order to do a simulation, a fancy simulation in 3D with a realistic representation of the robot. But I think that this was realistic enough if you look at the actor robot. Now, the task, as you can see, is going from one position to another position in the Cartesian space, but taking into account also the orientation. In fact, you see an initial orientation frame and a final orientation frame. Now, the reason why I'm showing this is because I would like you, if we are able to achieve some interaction from home with me, I would like to comment on the way in which the error goes to zero in this case. Okay, so let's look at the simulation. I hope it starts. Yes. Now this is a simulation in time. Okay, so let's look at it again. So this is a full 6-dimensional task, so position and orientation. What do you notice in this transient behavior? Any comment? So first of all, the path, I'm running this over and over. The path is really a linear path joining the initial position to the final position. So probably, I think I have planned a motion going in straight line there, and probably with a rotation for the end effector. Is this what happened? Why the robot is slowing down so embarrassingly at the end? Okay, there is a steady state error. There's no steady state error. No steady state error. No. There's a slow approach. The smaller the error becomes, the slower it's going to be reduced, which is exactly the principle of exponential convergence. An exponential goes quite fast at the beginning, but then slows down just because its derivative is going down. Eventually it goes to zero, but only for t going to infinity. In practice, I mean, the visualization shows that we have steady state error. So it seems that there's a dynamic here of the error which is purely exponential. Has nothing to do with the time in which I'm completing the task. In fact, in this simulation, there were no feed-forward terms. So there were only the error was driving the motion. So the robot was starting from the beginning, from this position and orientation. And now it sees only an error getting to the final position and orientation. And because we have a compensation in the Cartesian space, control in the Cartesian space, it goes along the straight line direction. There was an error only in the, let's say, z and y coordinate, no error on the x. So on the x, there's no error at all. So the end effector goes straight to the destination. And similarly for the orientation. But because we have not planned the trajectory here, we are only driven by the error, and we see the full error at the beginning, and then we reduce the error, the transient will be exponential, so we not have a pre-planned time for doing the task. In the previous simulation that we have seen, we have said, okay, I have to go along this straight line with 2 meters per second. So the whole should be completed in whatever, in 1 second, in 2 seconds, whatever. So we are assigning a motion and a desired timing law. So if the error is 0, we will move exactly as we plan. If it's not 0, we have to compensate for the error in the initial transient, but eventually we will move there. So I will complete the motion. If not in the nominal, let's say 1 second, I will complete it in 1.05 seconds and so on. But I will complete this in finite time. While without the feed forward, I'm only relying on the error driving my motion. And the best I can do is to bring the error exponentially to 0. There's no finite time solution in the continuous world. Okay, so this is why it is moving in this way. I think that this is very, I mean, I leave this video and this slide without any comment because I would like you to reason about this. Okay, so this is why I was asking. Now, the last slide is some experiment that we performed a few years ago in the lab when the KUKA lightweight robot was just arrived. And, well, there's a lot of things here, but the message that I would like to convey to you, or the result, is that here we are using kinematic control for the robot. And in particular, we are commanding in velocity the joints. We can command also in acceleration the joints. Indeed, the acceleration command is more complex. And here, but pursues some other criteria. I mean, in resolving the redundancy, in this case, we have to follow a Cartesian path in position only. So the task is three-dimensional. And the robot has 7 degrees of freedom. So there is redundancy enough. And we can optimize some criterion. There are several things that you can do. And if you work at the acceleration level, you may take into account also some dynamic effect. So the acceleration control is more rich, but it's more hard to compute. So in this paper, we proposed a way to approximate the acceleration control with the velocity command. So doing at the first order level what the acceleration controller would have done at the second order level, okay? So in fact, we are optimizing torque locally and so on, so things that are intrinsically dynamics. Okay, let's see what happened. No, I've spoken enough. So piecewise linear trajectory going through 4 Cartesian points. So a kind of a square, and you can see the parallel simulation and experimentation. And the robot would stop at some point because the velocity commands that we are commanding to the low-level control loop would violate some limits. So we repeat this at the acceleration level, so with a smoother command, and we are able to trace the 3-segment path. Now, we would like to execute the same thing at the velocity level, but in a different way. So trying to mimic what the acceleration command is doing, so never exceeding limits that would bring the robot into a safety protection condition. And here you see a very nice, I mean, the robot is orange, but you see the green and the blue version, which is the acceleration level controller, which works fine, but it's more complex. And here our velocity control, which is simpler and mimics exactly the same behavior. And if you look at the differences in terms of the acceleration computed with the acceleration level controller and our discrete time version of velocity level, mimicking the acceleration one, you can see on the left-hand plots that the error is below 10 to the minus 3 radian per second square. And the mounting of this video is quite nice because you see that the actual experiment and their reproduction in MATLAB to show the actual plot of the data. And this has been done in real time, in fact. Okay, so that was it. And this completes our lecture and our course. I hope you enjoyed, despite the fact that you were not here and the interaction was kind of limited. I'm sorry for that. I could have done a better job, but we hope that this situation will not last too long. Okay, let me go out of here.